Here we go. So here's the plan with related rates. Usually we've got a situation that describes two or more things changing with respect to time. So we try to draw a diagram, and the things that are growing or getting smaller are going to be labeled with variables. And then we try to write an equation that relates those variables at any time t. We'll take the derivative of it, and we get our related rates equation that has our variables in it and our rates of change with it. And then we fill in the numbers at the very end. So here we go on problem number 7. You still have the handouts? Yep. So I don't have to write the whole thing. I can just kind of read it and draw it. A water tank has the shape of an inverted right circular cone. That means the point is at the bottom when they say inverted. So it looks like a cone. That is an awesome cone. Until I got to the point, I got all screwy. The altitude of the cone is 12 feet. The base radius is 6 feet. Water is being pumped into the tank at a rate of 10 gallons per minute. Find the rate at which the water level is rising. So let's put this as the water level. We'll call it Y. Find the rate at which the water level is rising when it is 3 feet deep. Find the rate, right? So you agree with the rate is the derivative of that thing that I named the water level? Find the rate at which the water level is rising when the water level is 3 feet deep. And then it says convert this gallon to cubic feet by saying 1 gallon is 0.134 cubic feet. So 10 gallons is, move the decimal over once. What is that cubic feet going to be a measure of? Volume. So this is this is 10 gallons per minute. So that's cubic feet per minute. That means that's the change in volume with respect to time. Find the change in the height with respect to time, given the change in volume with respect to time. So I should have called that H instead of Y, right? Because our volume formula for a right circular cone, who knows that one? Anything with a point has a 1/3. And then the circular top gives us the pi r squared, and then the H. So let's make Y into an H. So we have dH dt. We'll find dH dt when H is 3. So we're going to start with the volume formula. Volume is equal to 1/3 pi r squared H. Is there a formula you don't know? Google it or ask me and I can give you the formula. We don't have any information given about R. So before I start taking derivatives, I'm going to see if there's some way for me to write R in terms of H. The R that we're talking about is the radius of the water level, not the radius of the cone. That's what's changing. So here's our R. Can you see anything that will help me write an equation to give me R as a function of H? We do have similar triangles again. We have the dimensions of the cone, the height and the radius, and then the height and the radius of the water. So in our similar triangles, we have this big triangle where this is 12 and that's 6, and this little triangle here where that's H and that's R. You can kind of see, based upon these two numbers, that the radius is going to be half of the height. But you can set up the proportions. 6 is to 12 as R is to H. So R, throughout this whole discussion, is going to be 1/2 H. So we can put that in where the R is and get volume strictly as a function of H, and then we can take derivatives. So when I put it in there, I've got to square it. And then multiply with the H. So let's clean that up. 1/2 squared is a 4. Times that 1/3 gives me 1/12. So I have my volume as a 1/12 pi. That's all a bunch of constants. Then I've got an H squared times an H. So I've got an H. So that'll be our starting equation. We're going to take that and take the derivative of it. So do the derivative for me. Keep in mind that 1/12 pi is just a constant. Factor it out. Take the derivative of the H cubed, put it back on. All right, so it's a quickie. This is what you should get after you take the derivative. On the left side, you get dv dt. Here's the factored out constant. And then the derivative of H cubed gives us a 3H squared dH dt. There's your related rates equation. Is that okay with everybody? Okay, let's see what numbers we have. We have H is going to be 3. We're looking to find this. And dv dt is 1.34. So fill it all in and let's solve for dH dt. H is 3. Let's see, I'm going to go ahead and simplify a little bit from that earlier step. 3 goes into 12 4 times. That's a 9 pi over 4 times dH dt is equal to 1.34. So multiply by 4, divide by 9 pi, and we should have it. I don't know what these numbers are. That's a positive number, which says that the water level is rising at that many feet per minute. That is your pencil. When you threw with me last time, you missed it yet. Can't turn my back on you. Get one right there. All right, what about these steps? Think they're logical steps to follow all that? And I suppose we'll do number 8. Number 8 says, block of ice in the shape of a cube, originally having a volume of 1,000 cubic centimeters, is melting in such a way that the length of each of its edges is decreasing at a rate of 2 centimeters per hour. At what rate is the surface area changing at the time when its volume is 64 cubic centimeters. Assume the block maintains its cubical shape. Well, we were given a lot of information. Let me draw the cube so I can stall and figure out what I'm going to do with all this information. It's a cube, meaning all of its sides have the same length. And the sides are changing, so let's put a variable there. Let's see that the sides all have a length of x by x by x centimeters. Okay, so original volume is 1,000 cubic centimeters. The length of each of its edges is decreasing at 2 centimeters per hour. We can make it negative since it's decreasing. And the length of the edges was x. That's going to be a change in x with respect to time. At what rate is the surface area changing? So let's let surface area be A. We want to find dA dt. What rate? When the volume is 64. The surface area is the sum of the areas of all the faces. So it's each face is a square that's x by x. It's a cube, so I have 6 faces. So surface area is just 6 times x squared. So once we have the starting equation, we'll go ahead and take the derivative of it and then see if we have enough information. So it's kind of a quick derivative. The left says dA dt is equal to 12x dx dt. And so do we have stuff to put in everywhere? Well, we got dx dt. What are we going to use for x at that instant? We can find it, all right. It's at the instant when the volume is 64. So what are the lengths of all the edges when the volume is 64? Volume is just the product of the 3 dimensions, right? 64 is just going to be x cubed. So what number do you cube to get 64? 4. X is going to be 4 at that instant. So on the right hand side, we have 12 times 4 times negative 2. (48 times 2 is a negative 96. What should the units be on that? Area is decreasing. So what are your units on area? Centimeters squared at a rate of 96 centimeters squared per hour.
Where did you get that?
This 6, each face has an area of x squared, and then I have a total of 6 faces. So that's all I got for you. Do you have anything that you want to ask about in terms of woodwork? Did you started on any of those? Oh. One of the early ones starts with some version of this formula and asks you to hold one of the items constant and find the derivative with respect to the other, and then eventually hold them all, take the derivative with respect to all of them. So let's kind of do something like that. So let's use this formula here. So if R is constant, find dV dt. Then we'll hold H constant, and then we'll run them both as variables. So when you're told R is a constant, then this R squared behaves like the pi and the 1/3. We just ignore it for now, take the derivative of both sides with respect to time, and then put the constants back on. So if I do that, that says that dV dt is equal to our constants times the derivative of that H, which is just dH dt. Now let's change the game. If H is constant, then what does dV dt equal to?
Would be 1/3 pi h to r er dt.
Perfect. Pull out the constant, take the derivative of the R, and you get that. What if neither is constant? They're all changing with respect to time. Like a normal derivative, what would be normal in this case? Be careful, we got a product. We've got to do the product rule.
So
Okay, so then use the product rule. Try it, write on your paper. Right, when they're constants, we factor them out, but if they change with time, then they're variables. So you've got to treat them as such and do the product rule. I had to factor out the 1/3 pi. And we'll put our product rule here. Who wants to call it out? What's it going to look like? Good. First times the derivative of the second plus the second times the derivative of the first. Okay, so that's what they're asking for, like on one of those earlier problems. Shall we try another?
I think, hold on, let's see. Okay, at noon, ship A
Right.
is 20 nautical miles west of ship B.
Okay.
Ship A is sailing west at 19 knots.
We're just gonna call that 19 miles per hour. Okay.
And B is sailing north at 18 knots. Or miles per hour.
Okay.
And then it's asking how fast in knots is the distance between ships changing at 7 p.m.
So this is at noon. How fast is the distance between them changing? Seven p.m. How do we measure the distance between them?
Use a triangle.
Yeah, it's gonna be the hypotenuse of this triangle here. This is changing right here. So we actually have three things that are changing with time. We've got both legs and the hypotenuse changing over time. So we'll need three variables. This is just this little piece in which we get a rate of change. So let's call this one X, and then we'll just add the 20 to it to get that side. So X is the distance that ship A has moved after 12. Y is going to be the distance that ship B moves after 12 o'clock. And then if I just continue going down my alphabet, I guess Z is the distance between them. So that 18 represents dy dt. The 19 is dx dt. And we're looking to find dz dt. So we're given dx dt is 19. dy dt is 18. We're asked to find dz dt at 7 p.m. So let's not worry about what we're going to do with the 7 p.m. just yet. Let's get an equation that relates those three variables. And remember, x is just this distance. So to figure this distance, I just add the 20. So from here to here is x plus 20. That's going to be y, and that one's going to be z. So we can use the Pythagorean theorem that says leg squared plus leg squared is the hypotenuse. Start with that. Take the derivative of it, and then we'll figure out if we need some more of these numbers from somewhere. My hint is that we're going to have to use that 7 p.m. eventually. Okay, so call out the derivative for me. Take the derivative all the way through here with respect to t. You'll call it out for me?
2 times x
Times what? Y times 1. Isn't X changing with time? Better? Okay, next one. Good. Good. So we're looking to find dz dt. We've got the dy dt and the dx dt, but we need an x and a y. So what I'd like you to do is figure out what the picture looks like at 7 p.m. Let 7 hours elapse. And tell me how long all of these guys are at 7 p.m. So here we go. Ship B is going 18 miles per hour for 7 hours. So 7 times 18. There you go. This is originally 20 miles, but now X is moving 19 miles per hour for 7 hours. Right, here's our mental math. We take 20 times 7 minus 1 times 7. 20 times 7 is 140. Minus 1 times 7 is 7. So 140 minus 7 is 133. Okay, and now we also are going to need Z, so that 133 plus 120, this is going to be my X right here. This is going to be my Y. But now we have to figure out Z using this whole length, this 153. So I have that Z is going to be a square root of that squared plus that squared. It's going 19 miles per hour for 7 hours. So 7 times 19. So Z is 153 squared plus 126 squared. We'll just leave it like that. But now we have numbers to put in everywhere. If you want, you can get rid of those 2's because we got 2's all the way across. You just divide both sides by 2, and that keeps one number out of our way. X plus 20 is this 153. Dx dt is 19. Y is the 126. Dy dt is the 18. Z is this number, and then we're going to solve for dz dt. So I have 153 times 19 plus 126 times 18 is equal to this funky number for Z. So all I'm going to do is divide by that. You can probably enter it like that into web work. That's a length, and so that's going to be miles per hour. Oh, we find one more. Maybe something that's not right triangle-ish. Let's see. Gonna get a web work opened here. All right, I think I'll work number 12. Let's see if I can show you number 12.
Before we move on, how did you find X and Y again?
I let 7 hours elapse because this was given to me at noon. Let 7 hours elapse at 19 miles per hour times 7. I get the 133. And then I let the Y was going at 18 miles per hour. So that was the 18 miles per hour times 7 hours. Okay. All right, so let me rub that off and see if you can read that problem here. Let me see if I can read it to where you can read it. Can you read that up there? Yes. Okay. Let me rub all this stuff off and we'll work it right here. So read it and let's see, they're giving us some hints here. Let's see if we can make sense out of it and set this up. Back up, that's way too close. Okay, airplane flies at a constant altitude. So let's go in at a certain height, 2 miles above, at 600 miles per hour. And somewhere it's going to pass this kangaroo on the ground. How fast is the angle of elevation between the kangaroo's line of sight increasing? Okay, so he's looking as it's coming. So the line of sight is here, and then it's increasing as the plane gets closer. So that's what we got to kind of draw. So construct a triangle representing the situation. Use this to get an equation first involving x and y. So x will be this way. I guess y, I don't know what they want y to be because it's at a constant altitude. So we'll have to figure out what they mean by y. Maybe y is the angle. I don't know. Why would they use y for an angle? Okay, so I don't know what a kangaroo looks like. Looks like a real fat rabbit.
Yes.
Okay. It's got popular. Kangaroo. I got the wrong calling, huh? I should have been in art. Unfortunately, my airplane looks just like that. This is my airplane. The thing's a little bit too close to the front, so it might have trouble flying. Ouch. I can do better. I promise I can do better.
There.
I'm really smiling over here. But look how large that kangaroo is compared to the airplane. But you got to remember perspective, that's 2 miles up. Well, this doesn't change. It stays at a constant altitude of 2 miles. Okay, but the closer the airplane gets to the rabbit, the line of sight is going to be from here. So assume that the line of sight is with the horizontal. Let's get the 2 miles to end there. So that angle is changing and this distance is changing. So I suppose that's what they want, X and Y. Does it matter to you where we put X? X should be with the X direction, huh? And this should be the Y. Y is how the angle getting bigger and bigger as the airplane gets closer. Okay, now let's see what we have. I've used the 2 miles. What are we going to do with that 600 miles per hour? What do you think that represents? dx dt. So dx dt is 600. Okay. How fast is the angle of elevation changing? So that's a find the dy dt. When the distance from the kangaroo to the plane is 3 miles, what's that going to be? When the distance from the kangaroo to the plane is 3 miles, that does sound like the hypotenuse, doesn't it? So I guess we're going to make that as another variable. And the distance between the kangaroo and the plane is 3 miles.
Would that be Y?
Well, it's not now. Yeah, I don't know what they mean by Y. But I think when Z is 3. I didn't want to involve Z. Let's save Z. And let's see if we can write an equation that relates, because we don't have a dz dt. So I don't want an equation that has a Z in it. I just want an equation that has an X and a Y in it.
So the 3 miles per second would be X, because it's still distance.
Not really. When they talk about distance, I think, well, is it? How can I say when the distance from the kangaroo to the plane is 3 miles? I think when the distance, because the plane is still going to be 2 miles up. So I think it is the Z. We'll be able to figure out X at that time. So can anybody give me an equation that relates X, Y, and maybe using the 2? Tangent. The tangent of Y is opposite over adjacent. So let's start with that one. And think of that 2 over X is 2 times X to the negative 1, because we need to take a derivative now. The derivative of the tangent is secant squared. I don't think kangaroos have long ears, do they? Maybe their ears are bent. Don't they bend? Does that look like a kangaroo?
They just have time.
You think they just have tiny ears?
They're very long.
That's better, huh?
They have small, like kind of dog-like things.
Do they? Okay.
Maybe a little bigger.
Oh, yeah, kind of like a deer.
There we go.
There we go. There we go. That's nice. Okay, there went my derivative, secant squared y dy dt. Now it's your turn. Take the derivative on the right-hand side.
Negative
-2.
X.
No, I'm gonna continue. What's the new power on x?
-2.
Now you tack on the dx dt, right? Ordinary derivative times the x prime term. Okay, so we got to solve for dy dt. We're going to figure out what x is when z is 3. And then we're going to use that to figure out what the secant of y is. So let's freeze frame everything and figure out this is 2, this is 3, we need x. It's not 1. X squared plus y squared is hypotenuse squared. Square root of 5. Square root of 5. Right? X squared plus 2 squared is 3 squared. So x squared plus 4 is 9. Says x squared is 5. So x is the square root of 5. And remember, this angle is y. I don't want to find out y exactly, but if I know the secant of y, I'm happy. So in that picture, what is the secant of y? Which two sides are we talking about? But
Like 1
no, it's not opposite. Secant is 1 over the cosine.
Oh, yeah, so 1 over x square root of 5 over 3.
The cosine would be square root of 5 over 3.
And 1 over.
So flip it, 3 over square root of 5. The hypotenuse over the adjacent. That's the secant of y. We'll put it in over there on the left-hand side and then square it. We're looking for dy dt. We've got x to be the square root of 5, and we have dx dt. So we've got numbers for everything now. I'm going to write this term here as -2 over x squared when I put the numbers in. So secant squared of y is going to be 3 over square root of 5 squared. We're looking for dy dt. And then I have -2 over x squared. The x was the square root of 5. And dx dt is 600. Probably should have made that 600 negative, right? Since that's getting smaller. And that way my angle would be growing. Right?
That's the speed.
Right, it's the change in x, but x is getting smaller. So I should make that a negative, so I'd have a negative times a negative to give my angle getting bigger. So let's do that. It's because it's getting smaller. I don't want my angle to get smaller. My angle's getting bigger as that plane gets closer. All right, so let's do the squaring. This is 9/5 times dy dt is equal to 1200 over 5. So I have to multiply by 5 over 9 to get the dy dt. I'm sorry?
2 is negative.
Well, that's why I put a negative here, so I have a negative positive. Because the angle's getting bigger. That bothered me, so I fixed it. Okay. Let's see, 9 and 12 are both divisible by 3. So I can make that 400 over 3. So dy dt is 400 over 3. Y is the angle, so we're going to call that radians per hour. If the angle grows by 400 over 3 radians per hour. Per minute? Was it 600 per minute?
Asking us to do it in radians per minute.
Ooh, so now I gotta change it to minutes? Because this is in hours. So if we want to change it now to minutes, I got radians per hour, so let's see. 400 divided by 3 radians per hour. And 1 hour is 60 minutes. That'll cancel the hours. So I can knock off a 0. And I have 40 over 18 radians per minute, which is 20 over 9. I think that might be our answer. 20 over 9 radians per minute. It should be. Let me see if they did it differently. Let's look at the, oh, it won't show me the steps. Here we go, solution. Do you have access to the key that says solution? Is that just me? Is that just my magical button? Let me see how they did it. So they got, oh, so see, they did use y to be the hypotenuse and not the angle. Gotcha. And so they got that, and then we get, and then they stick the angle in there. Huh. Converting hours to minutes gives blah, blah, blah. Okay. I think I'd rather call it the angle, right? You have to like the way I do it better because I just said you had to. All right, so I'm gonna put this out. You ready to go on to another section? We're moving too fast for any of y'all? Okay. Got one more section in chapter 3. So 3.8. It's something called the linear approximation. And it involves something called the differential. I'm going to draw part of a graph. I'm going to draw part of a graph that's just concave upward. The rest of the graph is doing a bunch of other stuff around it, but this is just a real close look at part of the graph. And then consider an ordered pair on the graph, say at A, f of A. One of the things that we've been doing over and over and over and over is writing the equation of the tangent line to the graph at the ordered pair A f of A. So let's do that real quick. Let me draw the tangent line here. I'm going to extend it out a bit. This is the tangent line. To y is equal to f of x at the ordered pair A f of A. Let's go ahead and write the equation of that tangent line. So it's a line, so it looks like y minus y1 is equal to m times x minus x1. And my y1 over there is just labeled f of A, and my x1 is the A, and then m is just going to be the derivative at x is a. So we'll have y minus f of a is equal to m, which is f prime at a, x minus a. And now let's solve this for y. I'll put the f of a in front. And the claim is for all points on the graph of y is equal to f of x, they're close enough to points on the tangent line that the points on the tangent line can better approximate them. So for instance, if I want to know, say I move over h units to a plus h, and I want to know the value of f of a plus h. Well, that y value is close enough to the y value on the tangent line. There goes my funky little leafy orange. That point there is going to be said to be the linear approximation to that y value there. I drew it large so they look far apart, but if this h is a small number, then these two y values are really close. So that's what we mean by linear approximation. If we want to approximate a more difficult value, f of a plus h, what we'll do is we'll just use this linear approximation. So instead of calling this y, I'm going to call it L of x. So our linear approximation to a point on y is equal to f of x, where this x is near a, is given by linear approximation for that particular x, and it's just the tangent line value right there. So this y value here is y is L of x. Call it a different name, but it's all telling us to do the same thing. So one typical example is, I know how to take real quickly the square root of 25. But suppose I wanted to approximate the square root of 25.7. Well, what I can do is find the equation of the tangent line to the square root function near the nice point, x is 25, and then my x minus a, which is essentially the change in x, would be the 0.7. So what shall we do that? So sometimes this is just written, here it was given by h, but sometimes this is just written as delta x. So for example, let's use this linear approximation to estimate the value of the square root of 25.7. So here's the graph of y is equal to the square root of x. We're going to go way out here to x is 25, write the equation of the tangent line. And then just move over on the tangent line to 25.7, find the value on the tangent line for that, and that's going to be approximately the value on the black curve. So here's L, and here's F. So in our example, F is the square root of x. I want to write the equation of the tangent line to the graph of y is equal to the square root of x at the point where x is 25. And then use that as my linear approximation.
What's that point label? 25
Square root of 25. So first, write the equation of the tangent line to y is equal to the square root of x at x is 25. So quick, what's the derivative of the square root of x in simplified form?
One over 2.
That's right. Derivative of the square root of x is 1 over 2 square root of x. Okay. So we need these values at x is 25. At x is 25, y is going to be 5, and y prime is going to be, well, you're putting a 25 in down here. Are you getting 110 for me? Now we're going to fill it in here. That's going to be 5 plus 1/10 times my x minus 25. So this is playing the role of the A. So you have my linear approximation is f of A. So f of 25 plus f prime at 25 times x minus 25. F of 25 we said was 5. F prime of 25 was 1/10. X minus 25 is here. And now our linear approximation says replace that x by 25.7. So next, the square root of 25.7 is roughly equal to the linear approximation of 25.7. So if you're now plugging that in right here, and we have 5 plus 1/10 of 25.7 minus 25. So that's a 0.7 in here. 0.7 is 7/10. 7/10 times 1/10 is 7 over 100, which is 0.07. So my linear approximation is that it's roughly equal to 5.07. Let's see how close we are. Got a calculator? Let's take quickly the square root of 25.7 and see if we're in the neighborhood. What is the actual square root of 25.7? 5.069. 5.069. Hey, that is not too shabby. And it was pretty easy. Okay. Okay, so why don't you approximate for me, doing the same idea, approximate for me 9.5 cubed. Well, let's make it closer to 10. How about 9.8 cubed? Approximate 9.8 cubed. So same instructions. Use the linear approximation to approximate 9.8 to the third power. using that linear approximation. Let's see if you can follow your train of thought. So what you're going to do is you're going to pick a point close to 9.8 that you can cube real easily. Even easier than that. 10 cubed is easy, right? There's still more zeros on there. So your A in this case is 10. You're going to write the equation of the tangent line to the graph of y is equal to x cubed at the point where x is 10. So that's how you start. Write the equation of the tangent line for y is x cubed. At the point where x is 10. Looks like I'm just blowing through your break. So what we'll do is I'll just let you out early. Right, this is our extra hour day. Good, and scared me there for a second. We're all late for our next class. All right, you got your equation of the tangent line yet? So y is equal to x cubed has as its derivative 3 times x squared. So we're going to have y minus y1, so 10 cubed is 1,000, is equal to m, 3 times 10 squared, x minus 10. So my tangent line would have 1,000 here, and my slope is 300. Instead of calling this y, we call that the linear approximation at any x near x is 10. So here's where we put in the 9.8. So the linear approximation at x is 9.8 is going to be 1,000 plus 300 times 9.8 minus 10. So 9.8 minus 10 is 0.2. That's 2/10, so that knocks off a 0. 0.2 times 300 then is going to be, and that's going to be a negative, right? So negative 0.2 times 300 is going to be a negative 60. So 940 is our approximate value. But this time, that's not going to be such a great approximation. What's 9.8 cubed exactly? $949? 41. Well, then it's not so bad. Point something?
Yeah, 0.492.
That's not so bad. I thought it would be worse because think of how steep the graph of y is equal to x cubed is. We're way up here when x is 10. Look, the slope was 300. A small change in x brings a huge change in y. So I thought we wouldn't be even that close. I thought we'd be off by, the tens place. So the linear approximation isn't so bad after all. Now, some of these things have names. Let me go back to my picture and label things. The distance between the x values is the change in x, or delta x. That's called the differential in x. So if I start at x is a and move over to x is a plus h, that's the differential in x, or the change in x. They're both the same. The differential is denoted with a d. dx is the differential in x. And this is the exact change in x. When x is the independent variable, its differential and its exact change are the same number. The exact change in y in this picture is this y value. That y value to that y value. So from here to here is the exact change in y, delta y. So delta y is the exact change in y. Its approximation is going to be the change in the tangent line. So the tangent line jumps from this y value to that y value. This distance between those two y values is called the differential in y. The differential in y is the amount of jump in the tangent line. And the differential in y is roughly equal to the change in y. Our change in y is right here. There's our change in y. That's delta y. This over here is called the differential in y. So this line can be rewritten to say that delta y, the exact change in y is the differential in y when they're close. So dy is f prime at a times our dx, or our delta x. And that makes sense, because look up here where I took the derivative. Y prime is 3x squared. Another way to write y prime is dy over dx is 3x squared. Now, if I treated this as if it were a fraction, and dx is a term that I can split apart, then I could just multiply by both sides by dx and get dy is 3x squared times dx. That's this part here. When you're in calculus 3, and if you're going to make it that far, you biology majors are going to get out of here after end of Cal 1. When you're in calculus 3, you have, instead of a graph in 2 dimensions, you have a surface. And so what you do is you write the equation of the plane that touches the surface at a point. So your x is still the independent variable, dx is the same as delta x, but now you're gonna have a change in the y direction and a change in the z direction to get you back on the plane. So you'll have a differential in y and a differential in z. And all you do is just add another term up here. But you won't be there because you're biology majors, you'll be dissecting mitochondria. Is that something that you could do? Oh, I spoke biology. Okay, so sometimes we're interested in approximating a change in y. Here we are interested in approximating a y value, period. But sometimes we're interested in approximating a change in a y value, which means we just compute this little bit piece right here. So let me see if I have an example that does that. Let's rub this off. Right. All right, let me see what I got. Let me see. Yeah. Okay, let's try this problem. The stopping distance of an automobile is given by the formula capital F of S is equal to 1.1 times S plus 0.054 times S squared, where capital F is a measurement in feet and little s is speed in miles per hour. Which doesn't make sense if I'm in feet and they're in miles, so there must have been some converting going on with those numbers. Estimate the change in stopping distance estimate the change in stopping distance when, I need my glasses, I can't read that. Change in stopping distance per additional miles per hour. Now, when S is 35 and when S is 55. You increase your speed by 20 miles per hour. How much does that increase your stopping distance? That's what that's saying. If you increase your speed from 35 miles per hour to 55 miles per hour, how does that affect your stopping distance? So you've got the brake slammed on, you're making that screeching noise. How much longer is your stopping distance? So we're estimating the change in stopping distance. The change in stopping distance in this problem is delta F. Our estimate is going to be dF, which is just that last part of the tangent line, the derivative times the change in x. It's going to be f prime times the change in x, or s in this case. But f prime is going to be a function of s. So we'll have to use one of those as our s that we're interested in. So we can, it doesn't matter which one, let's just use s as 35. So we want to compute this when s is 35 and delta s is 20, the difference between the 35 and the 55. So let's go over there and take the derivative. Plug it in where the f prime is, but put the 35 in for the s. Derivative times delta s. So our derivative, let's just do it over here. Capital F prime at any s is 1.1 plus, now I'm going to multiply that number by 2. 2 times 4 is 8, 2 times 5 is 10. So 0.108 times s. So we have that change in stopping distance is roughly equal to that's df, which is 1.1 plus 0.108 times, I said let's use 35 as s. So that's the f prime. Now times the delta s is 20. Let me multiply these out. 108 is 35. And then 3 decimal places. This number here is 3.78. Add 1.1 to that. It's 4.88 times 20. So let's multiply 488 by 20. Two decimal places is 97.6. 97.6 what? What are the units on DF? What is in feet? So it's feet per change in miles per hour. Right? If you're going to change your speed by 20 miles per hour, expect 97.6 more feet in your stopping distance. If you want the exact stopping distance, the exact change in stopping distance, is this at 55 miles per hour minus that at 35 miles per hour. But that involves squaring those numbers and then multiplying. So that's a messy calculation. With this one, I was able to do standing right there in front of you. Okay, so you got to pay attention to what it is that you're approximating. Are you going to approximate a single y value? Then you use the whole tangent line. Or are you going to approximate a change in y value, in which case you just use the last part of the tangent line, the slope times the change in the independent variable. Okay? So I've given it both ways to you on your web work. Either you're approximating a single change in y or a change in the independent variable. That's not very visible, is it? Remote. That's my remote. Oop, wrong way. That's what all I wrote. Do that one. That's the next section. Okay, so let's just do a little tiny example. Sure, let's go for markers today. Leaving them uncovered. Let y be equal to x to the fourth minus 3x squared plus 5x plus 4. Let's see, what I want you to do is approximate the change in y. That's the one that's delta y. The next changes. Excuse me. Thank you. From x is equal to 1 to x is equal to 1.01. Approximate the change in y when x changes from x is 1 to x is 1.01. So the exact change in y, delta y, the exact change in y is the value of this function here at the new x minus the value of that function at the original x. So look how messy that would be to compute. So it's the value of this thing at 1.01. That's y2. minus y1. So y1's not so bad. That's just 1 to the 4th minus 3 times 1 squared plus 5 times 1 plus 4. That's the exact change in y. This part's easy to figure. This part involves some messy calculations. So it says, don't do that. Let's use delta dy. dy is our approximation for delta y, where dy is going to be the derivative of y times the change in x. The derivative of y at the nice point. So we're going to use the 1. The derivative of y is just 4x cubed minus 6x plus 5. That's going to go right here. And then dx is the x2 minus x1, right? So I'll put the derivative here, 4 times x cubed minus 6 times x plus 5. But instead of the x, we use the nice x value. And then the delta x is just going to be messy x minus the nice x. Right, even I can compute that. 1 cubed is 1 times 4 is 4, minus 6 is a negative 2. Negative 2 plus 5 is 3, times 0.01 is 0.03. Delta y is roughly equal to 0.03. Let's check. We've got a calculator in here. Somebody give me this number I got already, or I can get. 1 minus 3 is negative 2. Negative 2 plus 9 is 7. And I need somebody with a calculator to give me this number. I can get 3. This is, I'm plugging 1 into the derivative. 4 minus 6 is negative 2 plus 5.
Oh,
Give me some extra numbers.
0, 3, 0, 4, 0.
All right, close enough. But look, after you subtract the 7, that's not a bad little approximation, isn't it? That a calculator. We've got 2 decimal places accuracy to the exact change in y. Okay? So that's essentially what we're doing here. We're looking at approximating a change in y by using the differential in y. And somebody says, well, what's the differential in y? It's y prime times dx. Or we're using the differential as part of the linear approximation to a function. We want to know the value of a function at a messy point. Well, we just use the value of a function at a near point on the tangent line. Okay? That's all we're doing. That's it. That's all. I don't think I gave you any that talks about percentage error, so I don't want to go through that. I think I'll stop there. Would that break your heart if I stop there? Yes? I heard somebody say yes. I heard somebody say, I don't break anybody's heart. Okay, what's going to happen in chapter 4 is we're going to be finding largest and smallest values of the function when compared to all other y values. And then we'll find largest and smallest values of functions when compared to just nearby y values. So we're going to be doing lots of derivatives and graphs. Sounds like fun? Chapter 4 probably is the meat of the course. All right, So that's what I want to do with you today. If you want to stick around and finish up some web work, I can stick around with you. If you want to leave, you can go ahead and leave. I won't take it personally.